We are going to apply Pascal's principle to a hydraulics problem. Hydraulic problems work if you have an incompressible fluid, and that's a fluid that whenever you compress it, it doesn't change its density. So here we have a car lift used in a service station. So in this compartment here, we've got an incompressible fluid. And what we're going to do over here is we're going to have compressed air, which is going to exert a force on a small piston right here with a circular cross-section having a radius of 5 centimeters. Okay? This pressure that's being exerted by this piston on this side of our apparatus, this pressure is transmitted by an incompressible liquid to a second piston over here that has a radius of 15 centimeters. And so our question for part A is how much or what force must the compressed air exert on this small piston right here in order to lift a car weighing 13,300 newtons. Okay, so A, we're looking for F1 equals question mark to lift 13,300 newtons on the other piston. Okay, so what we have here is we're going to have a force being exerted by some compressed air right here on this piston. That force is going to move this piston down here some distance that I'm going to call delta x1. Okay, so the piston's going to move to a new location here. Okay, so we're exerting the force here. We're displacing some volume. If this fluid is incompressible, then that means that we have to displace the same volume over here with the fluid, and so that's going to raise over here this piston up some distance, which I'm going to call delta x2. Okay, and so sitting on top of that piston is like a pedestal onto which the car is sitting, and that car has a weight of 13,300 newtons. So how much force do we need to apply in order to raise this car over here of weight 13,300 newtons? Okay, so what force do we need to apply? Well, we're going to apply Pascal's principle in order to solve this problem. Pascal's principle tells us that in an incompressible fluid, the pressure that we apply over here has to equal the pressure on this piston here, okay? And that only works if you have an incompressible fluid. So the pressure over here on piston 1 has to equal the pressure over here on our output piston, piston 2, okay? And we know that pressure is a force per area. So that means the force applied to our first piston divided by the cross-sectional area right here of that circular cross-sectional piston has to equal the output force, the force that's exerting upward over here, divided by the cross-sectional area of that piston. Okay, so we're looking for F1. So if we solve this equation for F1, F1 is equal to A1 over A2 times F2. So in this case, the area, the cross-sectional area of our first piston, which is pi times its radius squared, r1 squared, divided by the area of our second piston here, so pi r2 squared, see the pi's cancel, times the force that we have to move on this piston. We need to lift this car with a weight of 13,300 newtons, so that's F2 here, okay? So we plug in these quantities. We've got R1 is 5 centimeters, we're squaring it, divided by R2, which is 15 centimeters. I'm squaring it, and it's okay that these are in centimeters because we've got centimeters squared on top, centimeters squared on the bottom, so those units will cancel. And we're going to multiply this whole thing by the force we have to move on the second piston, which is 13,300 newtons. So then the force we must apply on our first piston over here, piston 1, has to equal 1.48 times 10 to the 3 newtons. So that's 1,480 newtons, okay? Well, let's talk about what this means here. We have to have the pressure on piston 1 equaling the pressure on piston 2 if our fluid is incompressible. So pressure is our force over area. So what that means is that our ratio of force over area has to be the same for both sides, okay? So on this side, we have a smaller amount of force that we have to apply to a smaller area. But as long as that ratio is the same as over here, this larger amount of force divided by this larger area, as long as those ratios are the same, then we're still able to satisfy this condition that the pressure applied to my first piston has to equal the pressure applied to our second piston. So it's pretty cool that in order to lift something that has a weight that's equivalent to this quantity right here, we can apply a smaller amount of force on the smaller cross section. And that's what we call mechanical advantage. We're using this hydraulic system here to our advantage. We get a smaller amount of input force, but we get a larger amount of output force. For part B, what air pressure will produce a force of this magnitude? Well, pressure is equal to force over area, so that's going to equal our force that has to be applied, 1,480 newtons, and then we divide that by the area of our piston, pi times r1 squared, so that's going to be 1,480 newtons divided by pi. This time we have to put our radius in meters, so 0.05 meters squared. Why? Well, because we have a newton, and a newton is a kilogram meter over a second squared. Okay, so whenever we do this, we get units of pascals for our pressure. If our distance here is in meters and our force is in newtons, and we find that that air pressure is equal to 1.88 times 10 to the 5 pascals, okay? And 1 atmosphere, the pressure that we experience at sea level is, so I'll call it the atmospheric pressure, is about 1.01 times 10 to the 5 pascals. So this is about almost twice the atmospheric pressure that we have to apply over here to get our piston, our second piston, to move a car of this weight here, okay? And then finally, we need to show that the work done by the input and output pistons are the same. So we need to show that work 1 is equal to work 2. The work that piston 1 does is equal to the work that piston 2 does, okay? So in order to show that they're equal to each other, you could also say that that's the same thing as saying that the ratio of the work done by the input piston divided by the work done by the output piston is equal to 1. So if they're both the same, their ratio is going to equal 1, okay? So remember, we can say that work is equal to a force times a distance. So I'm going to write this as F times delta X. Okay, so over here, we said that when we apply a force on this first piston, we have to move it some distance, delta X, in order to displace some volume of fluid, okay? That same volume of fluid is the volume of fluid that gets displaced over here to move our piston upward, okay? That volume is the same if we have an incompressible fluid. So we can relate the volume here that we have to displace for piston 1 of the fluid to the volume that we have to displace for piston 2 of the fluid. Those volumes are the same. So volume 1 is equal to volume 2. So the volume of fluid that our first piston is displacing is equal to the cross-sectional area of that piston times delta, what I'll call delta X1, which is the distance that that piston has to push downward on the fluid. So we'll say A1 times delta X1 has to equal, okay, the volume that has to be displaced in order to move the second piston up is going to equal the cross-sectional area of that piston times this distance, delta X, that the piston moves when this piston over here displaces the fluid. And so this will be A2 times delta X2. Okay? So the reason why I did that is because if we look back at this ratio, we can say that W1 over W2 is equal to F1 times delta X1 over F2 times delta X2. So from this expression, I can derive an expression that relates delta X1 to delta X2. So if I solve this over here for delta X1 over delta X2, I find that delta X1 over delta X2 equals A2 over A1. So this is equal to F1 over F2 times A2 over A1. Okay? Now, we also can derive a relationship here between F1 and F2. So here we've got F1 over A1 equals F2 over A2. So if I solve this ratio for F1 over A2, we find that F1 over F2 equals A1 over A2. And I'll leave it to you to prove to yourself that that is in fact what it is equal to. You just I'll let you do those algebra steps if you would like to prove to yourself that what I just said here is true. Okay? So then I can replace in here where I see F1 over F2, and I'll do it down here. F1 over F2 we saw is A1 over A2, and then we're going to multiply it by this ratio A2 over A1. So these terms cancel with each other, and so we just we just proved that W1 over W2 equals 1. And that's the same thing as saying that the work done by the input piston is equal to the work done by the output piston. Or another way you could solve this problem is right here at this step, okay, you could go ahead and plug in what we know for F1 and F2. We know what F2 has to be, that's 13,300 newtons. We found what F1 is equal to, that's 1,480 newtons, and we already know A2 and A1. So you could plug in those quantities here, and whenever you do that, this F1 times A2 divided by F2 times A1 should also equal 1.